In this video, I'm going to explain the concept of Gibbs free energy and how we can use it to determine if a reaction is spontaneous or not. So Gibbs free energy that we show it with symbol G is defined as energy that is free to do work, and it's equal to H minus Ts. That G is Gibbs free energy, H is enthalpy. That in my previous video I explained what's H and what's delta H. T is temperature in Kelvin, and S is entropy. To understand Gibbs free energy, firstly, I briefly explain what's entropy. Entropy of a system is the number of ways energy is distributed through a system. If you look at this image, on the image on left side, you see I put all physics book on right side. This side is all physics book, and this side I put all chemistry book. So as you can see, I don't have many options. I can put physics books on right side, right, and left, and chemistry book on left side, or I can put physics book on left side and chemistry book on right side. If I want to put this book randomly, I have many options to put them together. For example, look at here. Here I put two physics book here, and then I put one chemistry book. Again, I put one physics book, and then I put the rest of chemistry book. And again, here I put one physics book, one chemistry book, and physics book, chemistry book, physics book, and chemistry book. And there are many other ways that I can put these books in this shelf. The entropy of this system is more than the entropy of system in this category. Here I have two options to put my books. Here I have more options. So entropy of system here is more than the other one. So think about it. Which one is easier? Putting books in two different parts, for example, always trying to put chemistry book in one side and physics book in other side, or just randomly putting our books there? Definitely putting the books randomly is easier. So, and it can happen spontaneously. If I want to put my books in two different sides, it means I need to think about it and I need to do work. It can't happen spontaneously. For organizing things, we need to do work. So it can't happen spontaneously. I think you learn the meaning of entropy. We know entropy of liquid is less than entropy of gas because gas molecules or gas particles have more freedom. If I name this one S of products or entropy of products, and this one entropy of reactants, then change of entropy, delta S, is S of product minus S of reactant. That in this case, because S of product is larger than S of reactant, so delta S is larger than 0. But if I have, for example, something in liquid state, and I want to convert it to solid, we know entropy of solid, S of solid of a substance, is less than S of liquid for that substance. Why? Because particles in solid state have less freedom to move. So as a result, delta S of this system is smaller than 0. Another example, let's see, we have CaCO3 solid. And I heat this one, and it gives me CaO solid plus CO2 gas. By looking at this one, you see this is S of your reactants, SR I show, and this one, I want to see S of product. I want to see if delta S of this system is larger than 0 or smaller than 0. You see here I have only one particle. Here I have 2 particles. So the number of particles increase in products, as well as that here we have gas. I have a gas, carbon dioxide, and a solid, but in the reactant part, I only have solid substance. So definitely delta S of this system has increased. Okay, right now I think you got some information, some understanding about entropy. So we go back to Gibbs free energy. So we learn about Gibbs free energy, or G, is equal H minus Ts. And we learned that G is Gibbs free energy, H is enthalpy, T is temperature in Kelvin, and S is entropy. But we usually use change of Gibbs free energy to discuss if a reaction is spontaneous or not. So I write delta G is equal delta H minus T delta S. We need to remember two things, that any reaction has two drivers. These two drivers are delta H and delta S. But how they affect which direction a reaction goes? We need to remember, if a system has less energy, it's more stable. For example, if I have this reactant, it's energy, time for a reaction. If my reactants are here and my products here, it means the gap between these two is delta H. And delta H of this system, as we learned in my previous video, is smaller than 0. And because reactants have more energy than products, so the system going towards a state with lower energy. And it's more stable. And we know everything likes to go towards stability. So all reaction likes to go towards a direction that delta H is smaller than 0. So remember, for a reaction to be spontaneous, delta H smaller than 0 is a positive. What about entropy? All system likes to go to the direction that entropy of system increases. As we talked about entropy, we know going toward disorder can be spontaneous. But if you want to put things in order, or decreasing, or if you want to decrease the entropy, you need to do work. You need to use some energy to to organize everything. Remember, a system likes to go towards the direction that its entropy increases. And as we discussed, if you want to put things in order or organize things, you need to do work. It can't happen spontaneously. Okay, so we have these two factors for a reaction. So we need to consider these two to discuss if a reaction is spontaneous or not. Okay, right now let's consider different types of reaction. If we have a reaction that delta H for that reaction is smaller than 0, and delta S is larger than 0. Definitely, delta H is smaller than 0. This is something that is in favor of reaction. Delta S larger than 0 is again in favor of reaction. So this reaction should be spontaneous. Let's look at the delta G. If delta H is smaller than 0 and delta S is larger than 0, it means it's positive. And time, when it's in Kelvin, is always positive. So positive times positive is positive, and times this negative is negative. So this part together is negative. Negative plus negative is negative. So delta G for this reaction is smaller than 0. So it means for a reaction to be spontaneous, delta G should be smaller than 0. So I write it here, delta G is smaller than 0 for a reaction to be spontaneous. So spontaneous. It means if I have delta G larger than 0, the reaction is non-spontaneous. And delta G equals 0 is equilibrium. That we discussed this one in another video. So if delta H is smaller than 0 and delta is larger than 0, definitely delta G is smaller than 0 and reaction is 100% spontaneous. But if delta H is larger than 0 and delta S is smaller than 0. Delta H larger than 0, it means that energy of product is more than energy of reactant. It's not something that reaction tend to do that. So it's not a positive things for a reaction. And delta S is smaller than 0. It means entropy of system is decreasing. Again, it's not a positive things for a reaction. So both of them are not in favor of reactions. Definitely, this reaction can't be spontaneous. But let's look at delta G. So delta G of this system should be larger than 0. Let's see if it is. So I write the formula delta G equal delta H minus T delta S. So as you can see, delta H larger than 0, so it's positive. Delta S is negative. T is positive. Negative times positive is negative, and then negative times negative, this part is positive. Positive and positive and positive, so delta G, when you add two positive numbers, definitely the answer is positive. So delta G is larger than 0, and definitely this reaction is non-spontaneous. Okay, so we discussed when delta H is smaller than 0, delta S is larger than 0. Both of them are in favor of reaction, so definitely the reaction is spontaneous and delta G is smaller than 0. If delta H is larger than 0 and delta S is smaller than 0, none of them are in favor of reaction. So delta G is larger than 0 and the reaction can't be spontaneous. Right now, we want to look at the third option, that delta H is larger than 0 and delta S also is larger than 0. In this case, you can see delta H larger than 0 is not in favor of reaction, but delta S larger than 0, it means entropy increasing, so it's in favor of reaction. So let's discuss delta G and see if this reaction can be spontaneous. So I write the formula for delta G one more time. And we look at this. So delta H is positive. Delta S also is positive. Positive times this negative becomes negative. And we know for a reaction to be spontaneous, delta G should be smaller than 0. How we can make delta G smaller than 0? By making this negative part larger. For making this larger, then we need to increase temperature. If we increase the temperature, it means the part that is T delta S become larger, and then because it's negative part, so this negative part plus delta H, the answer becomes negative. So this reaction can be spontaneous at high temperature. At high temperature. How high? If we have the amount of delta S and delta H, we can calculate what's that temperature that this reaction is spontaneous at it. Let's look at the last option, when delta H is smaller than 0 and delta S also is smaller than 0. In this case, you see delta H smaller than 0 is in favor of reaction. Delta S smaller than 0 is not in favor of reaction because entropy is decreasing. Okay, again, we need to see if it's possible for this reaction to be spontaneous. I write equation for delta G one more time. And we look at this. So delta H is smaller than 0. So this part is negative. Delta S also is smaller than 0. So it's negative. But negative times negative makes this part positive. To make delta G negative, because we know for a reaction to be spontaneous, delta G should be smaller than 0. To make this negative, we need to make this positive part small. How we can make it small? By decreasing temperature. So I can say this reaction is spontaneous at low temperature, at low T. Remember how low, for example, what's the actual temperature that this reaction is spontaneous? You can calculate that if you know the amount of delta S and delta H of reaction. Okay, so to summarize, you remember sometimes reactions are always spontaneous. Sometimes the reaction is not spontaneous at all. And sometimes when one driver is in favor of reaction and the other is not, then if the reaction can be spontaneous or not depends on the temperature. Let's look at some example. This reaction, N2 plus 3H2 give us 2NH3. Delta H of this reaction is smaller than 0. So as you can see, delta H is in favor of reaction. But let's look at the entropy. Here I have 1 mole of gas plus 3 mole of gas is 4 mole of gas. But other side, I have only 2 moles of gases. You see the number of particles decreasing. So it means entropy of products is less than entropy of our reactants. It means delta S of system is decreasing. So, okay, as you can see, delta H is in favor of reaction, but delta S is not. So I write the equation for delta G again. And we know for a reaction to be spontaneous, delta G should be smaller than 0. As you can see, delta H here is negative, and delta S also is negative. And so, because here we have a negative, so this part, negative times negative, become positive. So for this reaction to be spontaneous, it means for delta G to be smaller than 0, the positive part should be small. So it means temperature should be low. So this reaction can be spontaneous at low temperature. Let's look at the other example. We have liquid water and we want to convert it to steam or gas. We know for doing that, we need to heat it. So delta H for this reaction definitely is larger than 0. However, you know liquid to gas, it means entropy of system increasing. So delta S is larger than 0. Again, you see delta H is not in favor of reaction, but delta S is. So we need to see at what temperature this reaction can be spontaneous. Again, we need to look at delta G equation, that is this, and then we say this part is positive and this part is also positive. But positive times this negative becomes negative. So for delta G to be smaller than 0, we need to make negative parts larger. It means this reaction can be spontaneous at high temperature. We look at one more example, that is H2O, liquid to solid. We know delta H for this reaction is smaller than 0. However, when you look at liquid to solid, it means delta S of system is decreasing. Again, one more time, we write delta G, delta H minus T delta S. And this one is negative, this one negative, negative times negative, positive. So for this reaction to be spontaneous, or for delta G to be smaller than 0, this part should be small, so T should be low. So this reaction is spontaneous at low temperature. I hope this video was helpful and thank you for watching.